Hello, this is Blair. Um, as I mentioned in the previous last two videos, we needed to break up the lecture videos because we've been having some technical difficulties. So we are going to finish up this week's lecture videos by covering 9.3, which is talking about dot product. So we're on this last bullet point essentially. Okay. So let's scroll through everything that we've already talked about. Let's see, almost there. Okay, we're here. Okay, now the dot product is a very interesting concept. So we have, when we take the dot product of two vectors, which it's different than multiplication. It's not multiplying two vectors. You actually can't multiply two vectors. But when you take the dot product of two vectors, you start with two vector quantities and you end up with a scalar quantity, just a number. Okay, it's just a real number. But either way, when we take the dot product, we denote it with this dot, just like how it sounds. When we take these two vectors, a0 and a1, dotted with b0 and b1, we're just going to multiply component-wise and add all of those multiples together. Okay, so when we're talking about this in a two-dimensional sense, we're only adding two of these together. But as vectors grow larger and larger and larger, you'd theoretically just keep on adding all of these multiples of the multiplications of the components. So there's nothing really to look at here. It's just kind of giving you a more of a visual idea of what a vector A and vector B is to basically liven up the slide. But let's at least talk about the properties of dot products. So assuming that we have three vectors, A, B, and D, and say we have a number, a scalar value, C, that's just any real number, then we have a commutative property. So this means that A dot B is equivalent to B dot A, and that's a very trivial one to show. We have a distributive property. So this means that A dot, the quantity of vector B plus D, is equivalent to A dot B plus A dot D. So we're just distributing through as a dot product to each of these terms. And then we also have a scalability property. So what the scalability property means is it does not really matter what we scale. We can scale vector A and then dot that result with vector B, or we can dot our A and our B quantities and then scale it, or we can take our vector A and dot it with our scaled version of vector B. Okay, so it doesn't really matter which we scale. They're all equivalent. Okay. Now this one's not really a property. It's listed in properties in your textbook, but it is slightly different. But we have our relationship to magnitude. So if we take the dot product of a vector with itself, this ends up just being the magnitude squared. And this is a very simple thing to show as well. Oh, and I just noticed that this has a typo. That should be multiplied, not added, right? A0, B0 plus A1, B1. So either way, if we were to look for just the magnitude of vector A right here, remember that this is that A0, this is that A1. Recall that we can say, using Pythagorean theorem, the magnitude squared is equal to A0 squared plus A1 squared. Okay. Contrarily, if we were to take A dot A, where A is this A0 A1, we'd be taking A0, so let's just write that out, A0 A1 dotted with A0 A1. So we're going to take A0 times A0 plus A1 times A1. Well, A0 times A0 is A0 squared, and A1 times A1 is A1 squared. So we can say that this result is equivalent to this result. So we can say that A dot A is equal to this magnitude squared, since they're both equal to the exact same result. Okay. So now this is, I know I haven't really been doing this to you guys much, but we're doing it twice in this at the end of this lecture video for 9.3, but I'm giving you some incomplete notes. So with this, we have a geometrical representation of the dot product that we still need to figure out. Okay, so we're assuming that we have vector A and vector B, and we can recognize that there's going to be an angle that's created between these two vectors. And we're going to say that this angle is a bidirectional angle. It doesn't really matter, and that's why there's the two-headed arrow between these two vectors. Okay, and this angle is between 0 and pi. So this means that we never have an angle that's greater than 180 degrees. That means that we always take the shortest route to define the angle between two vectors. But that means that we could say that this is angle theta, or we could say that this is angle theta. It doesn't really matter. We're just saying that it's a relative angle between the two. So how large and how largely they're separated from one another. Okay. So now we can define and we can decompose vector A and vector B. So as a reminder, we could decompose vector A into the magnitude of vector A multiplied by, or scaling the vector cosine theta, or cosine alpha, sine alpha, right? Because that alpha is this angle, okay? And recall this would be a unit vector. Okay, we had already talked about that as well. Similarly, we could say vector B is going to be the magnitude of vector B scaling the unit vector cosine of beta sine of beta. Okay. Now what we want to do is we want to find a result for A dot B that relates everything geometrically. Okay. So we can say that A dot B is going to be this decomposed vector A dotted with this decomposed vector B. Okay. Now, using our scalability property, we know that we can scale any result of a dot product whenever. So we're just going to pull those out, these scalars, out all the way to the front, right? These are scalars. It's just the length of a vector. That's just a scalar property. It's not, doesn't reproduce a new vector. It's just the length, okay? And then we're going to take cosine of alpha, sine of alpha, and dot that with cosine of beta, sine of beta. Okay. Now we are going to multiply component-wise. So first components multiplied by each other, cosine of alpha, cosine of beta, and then we're going to add that to the multiplication of the second components. So plus sine of alpha, sine of beta. Okay, now this is where this may come back to haunt you a little bit. We have trigonometric identities coming back again. Okay. So cosine of some angle times cosine of another angle plus sine of some angle times sine of another angle. This is just kind of follows that tune that I had mentioned to you guys in class. So we have sine, cosine, cosine, sine, cosine, cosine, sine, sine, right? And that clap is where we change the sign. Well, we had that cosine, cosine, sine, sine. That's where we change the sign. So this is a sum and difference identity. Okay, so our result is going to be magnitude of vector A multiplied by magnitude of vector B take cosine of alpha minus beta. And if you have to look back up the identity, go ahead. You can pause the video for a second and look back up the identity, but that is the result. Okay. Now, what we need to do is we need to figure out, well, what is alpha and beta? Okay. Well, alpha is this angle right here, and beta is this smaller angle right here. So when we take alpha minus beta, we just end up with that theta, the angle between the two vectors. So we can come up with this result that we have A dot B is equal to the magnitude of the two vectors multiplied by each other, multiplied by cosine of the angle between the two vectors. Okay. Now there's a result that we can get from this. Or there's not a result, it's a known property that we get from a dot product, okay? So if we know that the dot product of two vectors is equal to 0, this is telling us that the two vectors are orthogonal, which just means that they're perpendicular, okay? And when things are perpendicular, this means that they're 90 degrees from one another, or pi halves from one another. That was a typo, okay? And there's two ways that we can think about showing this. The first way, we can say A dot B is equal to some scalar. We're just going to say that this entire thing is just some scalar, okay, times cosine of 90 degrees. Well, cosine of 90 degrees is 0, and so A dot B is equal to 0. Okay, so there's a very trivial and easy way to show that A dot B is equal to 0 when we're at 90 degrees. Or there's a more concrete way of showing this. Okay, we can solve for what theta actually satisfies this. So we can resolve and substitute, and this is actually a theorem in your textbook. I just don't think it's very important because I feel like this is important enough. There's no reason to have to maneuver things around in order to solve for the exact same thing, essentially. So we could say cosine of theta, if we were solving for theta, is equal to A dot B over magnitude of A multiplied by magnitude of B. And if you guys want to memorize that or use this, that's totally fine by me, but it's essentially the same thing as just using this down here, just by moving components around. But either way, when we solve for which theta satisfies A dot B to be equal to 0, we're going to get 0 over some number, and so ultimately we're just looking for when theta is equal to cosine inverse of 0. Well, this ends up being at pi halves when we kind of brush off the spider webs from inverse trig, okay? Because our from inverse trigonometry, our let's see, our range for inverse cosine ends up going from 0 to pi. So I had to think about it for a second. It's been a little bit for me too. Okay. So if it's from 0 to pi, it's only equal to 0 at pi halves. It's also equal to 0 at 3 pi halves, right? But that's outside of the range. So it's pi halves. Okay. Now we're going to talk about orthogonal projections. Okay. So now that we have knowledge of dot product and we have a knowledge of orthogonality, and also note, this doesn't mean that we have two ways to solve a dot product now, is what it's saying. So A dot B would be equal to A naught B naught plus A1 B1. So that would be way one. And our second way would be A dot B is equal to this geometrical representation. So it really depends on what you know and what you don't know. Okay, so if you know the angle and you know one of the vectors, then you could solve for another vector. Or if you know the vectors and you don't know the angles, you could solve for each of the magnitudes. It's actually not right. We could solve for the magnitude of A, magnitude of B. We could solve A dot B using this first representation. And then now we know this component, we know these values, and we can then solve for theta using inverse trig. Okay, so you just kind of use both of them interchangeably. Okay, now back down to orthogonal projections. Sorry to get sidetracked. So now that we have a deeper knowledge on dot product and a deeper knowledge on orthogonality, we can use both to project a vector onto a new vector. And we can kind of think of this as like a shadow. If we were to kind of think of like maybe like a sun up here. How the sun would basically cast a shadow of vector A onto vector B. Okay, and what that means is that we are going to just create this orthogonal projection onto vector B to create this new vector right here. Okay, and how we read this is we say that this is the projection of vector A on to vector B. Okay, so it points in the direction of vector B. Okay, and we can, for the sake of this this proof, we're going to label it vector V so that we don't have to keep on referring to it as projection of B parentheses A. Okay, so we're going to refer to it to vector V. But now what we're going to do is we're going to take that triangle and we're going to get a relationship out of this. Okay, because we can relate this angle between these two vectors. And we're going to be talking about vector V now because that's what's composing this right triangle. So we can take this, find a relationship between these two vectors and its angle between the two. So we can say that cosine of theta is equal to V, so adjacent, over A, hypotenuse. And that's just the lengths of these guys, right? The magnitudes. So then we can then say that V, by multiplying the magnitude of A over, is equal to the magnitude of A multiplied by cosine of theta. Okay, now we've already found what cosine of theta is. I'm going to scroll up slightly just to get a copy of this. So we've already said that cosine of theta is equal to A dot B over the magnitude of A times the magnitude of B. Okay, and this is also equivalent to, right, B and V are both pointing in the exact same direction, so this has the exact same relationship. But we want this B vector to be in our notation because we don't know what V is. V is what we're looking for. So we can say that A multiplied by A dot B over the magnitude of A times the magnitude of B, okay, where these magnitudes of A's just cancel out, okay. But now what we notice is that we've found the length of this projection. We haven't found the projection itself. So we need another kind of tricky step, and this step really is tricky. So if you don't quite follow this next step, don't worry about it too much. I'm doing it in a different color to kind of indicate this is the tricky step. But this is what's happening, okay? So we know that since B and V are pointing in the exact same direction, we know that we can create a unit vector right here. And we can create this unit vector two different ways. We can say that we want to take B and scale it down by its magnitude. Or we can take this new vector V that we're creating, this projected vector, and scale it down by its vector, right? Because they're both pointing in the same direction, okay? So now, when we take this result, since we know that these two are equivalent, we can say we're looking for this vector V. So this vector V is going to be the magnitude of V multiplied by this vector B, which is our known vector, right? V is what we're looking for. And so it's going to be equivalent to this, okay? Well, we know this magnitude of V. That's what we've solved for up here. Okay, so now we can kind of go back to our other color. Now we're kind of out of the tricky component. So we can substitute in that magnitude of vector V. So this is going to be vector A dot vector B divided by magnitude of vector B. And this is going to be scaling vector B over magnitude of b. Okay, well, we can multiply these two denominators together, okay, because magnitude of b multiplied by the magnitude of b ends up just being the magnitude of b squared. So we can just pull it onto the inside, okay? So this v, this result of this v, this vector v that we solved for, is the projection of a onto b. So a onto b, which ends up being a dot b, which is a scalar, right? Dot product creates a scalar, over the magnitude of b squared, which is also a scalar, right? Because the length of a vector is a scalar, and you square a scalar to get a scalar. And then we're taking the scalar and we're scaling vector b. So our projection ends up being the scaled vector, okay? And it's in the direction of vector b because we've scaled the vector b, okay? So hopefully that makes some sense. And before I move on to the last slide, I'm just going to double check to make sure that I didn't make any mistakes by comparing to the book. Yep, we're good. Okay, and that is how we use the result of orthogonality and dot product in order to create these orthogonal projections. Okay, now lastly, for story problems that you'll need is how we think about dot products in a physical practice. So when we think of physical practice, we usually think physics. Okay, so we can use a dot product to describe work that is performed in a physical sense. So we can say this nice little schematic that I found on Google. We have this person pulling a weight at some angle by a rope, okay? And so we can say that there's a force vector that is pulling on that rope by some magnitude, however much force he's pulling it on. So it could be 100 newtons in this angle or in this direction, okay? And that constitutes a magnitude, right? I mean, not a magnitude, a vector, right? It's a magnitude, it's some amount of force in some direction, okay? And he pulls at some distance, so from some starting point A to some starting point B, okay? We can, if we know, or to some ending point B. So if we know the starting point and the ending point, we can create a vector from A to B, okay? So the magnitude would be the distance, and the direction would be how you find the direction. A lot of the time, if it's someone's walking on the ground or pulling it along this ground, if it's flat, then that direction is just 0 degrees, or the y components are the exact same, right? Only the x components are changing. So this vector could be, from this schematic, it could be like equal to, say, 50, 0 meters. Maybe he pulled it to the right by 50 meters and nothing, no direction up or down. Okay, but what defines work? And this is just an example. Okay, but what defines work is the work to produce to apply a force vector to an object to move it to a desired distance vector from point A to point B, and this produces a scalar quantity. So work is just the force vector dotted with our AB vector, okay? And that is it for chapter 9 and everything that we are covering on vectors. I think I actually forgot to mention at the beginning of the very first video, we are not doing 9.4 and 9.5 that got decided to get removed. One thing that I did forget to mention though is the key phrase, because I mentioned it 3 other times in the other takes on these lecture videos. So the key phrase, we're following the exact same concept or the exact same theme as the other past 2 lecture video weeks worth of lecture videos that its Netflix series shows. This one's actually, I believe, a Showtime show, I want to say, but really good show. It's called Shameless. If you haven't seen it, another one that I highly suggest. Main actor is Fiona Gallagher. So Fiona is our key phrase. Okay, and that is it for this week. I will get to you guys later in the week with some example videos for the problems. Okay, bye.